Let's see what the second derivative tells us about the shape of a graph. As we're looking at these two functions, continuous functions, differentiable functions on the interval from a to b, and they are both increasing on this interval, both f and g. But as we look at the slopes of the tangents to the curve of these two different functions, one thing I notice for f is that the slopes of the tangents are getting larger. They are increasing in slope. Here, even though the function is increasing, the slopes of the tangents to the curve are getting smaller. They're still positive, but it's not as large near b as it is near a. And on this first function, you can see that the slope is smaller at a, and they've increased, and it's a larger value near b. This first function is called concave up, so it describes the shape of the graph. The second one is called concave down. So as the derivative is decreasing here, we'll have this concave down, still positive but getting smaller. The derivative increases as we move along here, and so we have a concave up. Notice for concave down, the function is always below the tangent to the curve, and notice for concave up, the function is always above the tangent to the curve. So this would be a way that we could define concavity with the tangent line, because it's a little hard to kind of put into words what concavity means in a technical sense, and we can define that. If the tangent is above the curve, then we've got our concave down, and if the tangents always end up below the curve, so the function is above, then we've got our concave up. And as we're looking at this, just a little short thing to kind of help you keep them straight if you had any issues, we always say concave up is like a cup and concave down is like a frown. So this is just like our little shapes, okay? Or they sometimes say concave up would hold water like a cup and concave down would not. So let's look at this graph and let's determine where it is concave up and where it is concave down. And we actually have it divided into intervals right now based on the concavity. So as we see from A to B, if you drew the tangent to the curve, it's always going to be above the function. This is concave down, so CD standing for concave down. You can see as we look from B to C, as we draw the tangent to the curve at any point along here, it's always going to be below the curve, and so we've got our concave up. And you can see from C to D, the tangent's going to be above. We've got our concave down. Tangent's going to be below here. We've got our concave up. And then concave up again, because tangent would be below it again, and then concave down. Let's look at our definition of concavity then. Let f be differentiable on an open interval I. If the derivative is increasing on the interval, then the function is concave up on the interval. So that's like we saw, it would be getting larger as we moved along. If the derivative is decreasing, then we have the function being concave down on the interval. If f is continuous at C and f changes concavity at C, so from up to down or from down to up, then we say f has an inflection point at C. So an inflection point are these points on the curve where we change concavity. So here is an example. Looking at this inflection point, we see that we're concave down to the left of it, then we change to concave up to the right of it, and the second derivative here happens to be 0. Now that's not a given that the second derivative has to be 0, we're going to see, but it happens to be on this continuous smooth curve. So we've got a test for concavity if the second derivative exists on the interval and if the second derivative is positive. Now remember, a second derivative positive, it's the derivative of the derivative. So what it tells us by a second derivative positive is it says the derivative is increasing, because we know a positive derivative tells us that the function is increasing. So the derivative function is increasing if the second derivative is positive. So then we would know it is concave up. If the second derivative is negative on the interval, so the derivative of the derivative negative tells us that the derivative function is decreasing, then we've got concave down. If C is a point on the interval and the second derivative equals 0 and the second derivative changes sign at C, then we have an inflection point at C. Notice some things it does not say that sometimes students mistakenly read into this. It does not say if the second derivative is 0, there's an inflection point. It says if the second derivative is 0 and the second derivative changes sign at C, then there's an inflection point. So second derivative equaling 0 is a candidate for an inflection point. Here's an example. If we found the second derivative of x to the fourth, we could take the first derivative by doing the power rule, power out in front, decrease the power by 1, and then we could take a derivative of that, so get the second derivative, and that's going to be 12x squared. And if we figured out where that equals 0, that's going to equal 0 at 0, but we see right here at 0, that is not an inflection point because this entire graph is concave up. It never does change concavity, and an inflection point is a point where it changes concavity. Another thing it does not say that for an inflection point to exist, the second derivative must equal 0. Let's look at an example of that. If we looked at f of x equals x to the 1/3, we can take the derivative, and the derivative is going to be power out in front, decrease the power by 1, and then we'll take a second derivative, and that's going to be power out in front, so that'll be negative 2/9, and decrease the power by 1, that's going to be negative 3/3 minus 2/3, so we got negative 5/3. I'm going to move above the graph here because I was kind of out of room there. I can express this as negative 2 over 9 x to the 5/3, getting rid of the negative exponent. So we see that we have x in the denominator on this second derivative, and so at 0 the second derivative is undefined. However, as we look at the graph, we see at 0 we have an inflection point. We have concave up over here to the left of 0. We have concave down over here to the right of 0, and so 0 is an inflection point, but the second derivative did not equal 0 there. So don't read too much into this. We know if the second derivative is positive on the interval, then the function is concave up on the interval. If the second derivative is negative on the interval, it's concave down. If C is a point in the interval and the second derivative is 0 and it changes signs, then we have an inflection point. So let's notice, as we say here, that at an inflection point the curve crosses its tangent there. Let's find our inflection points. We've got one at B, and if we made the tangent to the curve there, the tangent crosses the curve. So at inflection points we do go across, which was one of those sort of when you tried to intuitively first define a tangent, you wouldn't think it could cross the curve, but indeed it does at these inflection points. Now, right here, the derivative doesn't exist because of our corner or cusp, and that's also true at E. If we're looking at P, the tangent there goes across as well. So the significance of this inflection point is that the rate of change has its maximum or minimum value there. So the derivative function itself has its maxes or mins then at these inflection points. Let's look at this first graph. We have the derivative equaling 0 and the second derivative being positive. So this derivative equaling 0 is a candidate for our maximum or our minimum because it's a critical point. The second derivative greater than 0 tells us that it's concave up. If the function is concave up here, then we know that we have a local minimum. Similarly, but in the other case, we again have the first derivative equals 0, so we have a critical point, but we have that the second derivative is less than 0, so we know that the graph is concave down there, and so that tells us that we have a local maximum. So we can put this together and we can have our second derivative test. Suppose that the second derivative is continuous on an open interval containing C with the first derivative being 0. If the first derivative is 0 and we have this continuous function on the open interval, then if the second derivative is positive, that tells us concave up, so that tells us we have a local minimum because concave up, there we go. If the second derivative is negative, we have a local maximum because concave down. And if the second derivative is 0, we don't know anything. We may be suspicious of something. We may think, well, if the second derivative is 0, we've probably got an inflection point there, but we would need to determine that still. It doesn't tell us just because the second derivative is 0 that we do have an inflection point. We don't know that. So this theorem is a direct result of our concavity theorem.